We left off our last video talking about how we wish we could solve that matrix equation for the variable matrix, because that would give us x, y, and z equals something. This was the matrix equation that we wrote. It came directly from our definition of matrix multiplication. The way we multiply matrices allows us to say that AX is equal to the left side of a system of equations. What we would like to be able to do, if these were not matrices but were just numbers, we would just divide both sides by A, right? But matrix division does not exist. And so if matrix division does not exist, we can't do that for matrices. Let's work through how we do deal with this. We need a couple identities first. The identity matrix, or we need a couple definitions first. First is the identity matrix. Any n by n matrix with ones on the main diagonal and zeros elsewhere. We denote it with I sub n, where n represents the dimension. So this 1 by 1 matrix, 2 by 2 matrix, 3 by 3 matrix, and so on. An important concept here is that if you multiply any matrix by an identity, you get that matrix back. So I don't care what the matrix is, as long as you can multiply it, you will, if you multiply it by a matrix, the dimensions have to match appropriately, but you will get that same matrix back. The inverse of an n by n matrix is the n by n matrix A inverse, such that A times A inverse will equal A inverse times A, and both of those will be, the product of both of those will be equal to the identity matrix. It is important to note that not every matrix has an inverse. The way we check to see if two matrices are indeed inverses of one another is we multiply them and see if we get the identity. We have to do it both ways. 1, 2, 4, 6. Let's multiply that. So we're going to do B times A first. Negative 3, 1, 2, negative 1/2. Well, first of all, we can multiply them because they're both 2 by 2. We will get a 2 by 2 matrix. The way we do it, remember, first row by first column. 1 times negative 3 plus 2 times 2. Then we multiply first row by the second column. 1 times 1 plus 2 times negative 1/2. Now we move down to our second row, back to the first column. 4 times negative 3 plus 6 times 2. Then second column for second row. 4 times 1 plus 6 times negative 1/2. That gives me 1. That gives me 0. Negative 12 plus 12 is 0. 4 plus negative 3 is 1. That is indeed equal to the identity matrix I. That doesn't mean they're inverses of one another. We do have to check the other way. A, B. Negative 3, 1, 2, negative 1/2. 1, 2, 4, 6. I'm going to save us a little bit of time here. We will get this identity matrix when we multiply those. Okay? That tells me that A is equal to B inverse, or you could say B is equal to A inverse. They come in pairs. They are inverses of one another. In this example, you were given the function and the matrix and its inverse. What if you only have the matrix and you want to find its inverse? Here are our steps for doing that. We write the new matrix with write a new matrix with A on the left and I on the right, and we divide it by a vertical bar. So we've got this new big matrix. We perform elementary row operations until we have I on the left side and B on the right side. This B that you find will be the inverse of the matrix that you started with. You should be at this point asking yourself, why are we talking about inverse matrices? I promise we'll get there. Find the inverse of this matrix. -3, 1, 2, -1/2. We write the identity matrix over here. Remember those elementary row operations? We need to do those again. Let's do -1/3 of row 1 and put it in row 1 to give me a 1 here. Okay. I'm going to copy that other guy over. Next, I'm going to do -2 times row 1 plus row 2 and put it in row 2. Leave the first row as it is. -2 times 1 plus 2 is 0. Gosh, that's going to be, this entry here is going to be -2 times -1/3 plus -1/2. So that is 2/3 minus 1/2, or 4/6 minus 1/6, or 3/6. So that'll be 1/6 as our final answer when we add those two. -2 times -1/3 plus 0 is positive 2/3. -2 times 0 plus 1 is 1. Come up here. Next, I want to get a 1 where that 1/6 is, so I'm going to multiply 6 times row 2. Put it in row 2 position. 0, 1. 6 times 2/3 is 4. 6 times 1 is 6. Last step here. We need to get a 0 where that -1/3 is. So we'll do 1/3 times row 2 plus row 1. And we're putting that in row 1. 1/3 times 0 plus 1 is 1. 1/3 times 1 plus -1/3 is 0. Here we need to do, I'm going to write this down, this step. 1/3 times 4 plus -1/3. 4/3 minus 1/3 is 3/3. Now we're going to do, for this one, we're going to do 1/3 times 6 plus 0. That's 2. That tells me that A inverse is 1, 2, 4, 6. Okay, so that's how we do that, find the inverse using row operations. Now let's get back to why we care about inverses. That's what this solving systems of equations using matrix inversion really boils down to. AX equals B. One thing that we could do is we can multiply both sides of this equation by A inverse B. I'm sorry, A inverse in the front. Matrix multiplication is not commutative, so where you put it in the equation has to stay the same. A inverse times B is not the same as B times A inverse. If I put it in the front on the left side, I have to put it in the front on the right side. Well, why might I do that? By definition, this is I times X is equal to A inverse times B. And by that note that was up when we defined identities, whenever you multiply any matrix by an identity, you just get that matrix. So now we have the matrix X, the variable matrix, will equal A inverse times B. If we can calculate A inverse times B, we have equality here. We should be able to read off values for our variable. Let me show you what I mean. Solve using matrix inversion. First step is to write the matrix equation. Write the variable or the coefficients, then the variables, and that will equal 4, 6, the constants. By our work above, this variable matrix xy will equal the inverse of the coefficient matrix times 4, 6. Well, one thing that we did find already was the inverse of this matrix. That's what we did above, this -3, 1, 2, -1. We found that inverse to be 1, 2, 4, 6 right here. That was what we found the inverse of. If you didn't already have that, you would have to find that inverse. That means xy is equal to the product of these two matrices. Be very careful with your notation here. -3, 1, 2, -1/2 is not equal to 1, 2, 4, 6. But the inverse of it is. So that's why I have this inverse notation up here. And then once I actually put that inverse in, I don't need that inverse notation anymore. Multiply these, remember rows by columns. 1 times 4 plus 2 times 6 will be row 1, column 1. Now I'm going to row 2, so I'm going down. 4 times 4 plus 6 times 6 equals 4 and 12 is 16. 16 plus 36 would be 52. Those are some big numbers there. xy equaling 1652 tells me x has to equal 16 and y has to equal 52. That's the only way for those matrices to be equal. I'm going to go up and I'm just going to double check those numbers. -3 times 16 would be -48 plus 52 is indeed 4. 2 times 16 would be 32. Half of 52 would be 26, so we have 32 minus 26 is 6. Those do work. The numbers just seemed really big, so I wanted to double check it. The last thing I want to work on here is, as far as matrix inversion, is using our calculator to find the inverse of a matrix. If you are using the calculator in ALEKS, for those of you who are using ALEKS, that's my students and some others, you can, here, let's go back here for a second. You can solve a matrix equation on your calculator because you can find the inverse of a matrix on your calculator. First, let's write the matrix equation. 3, 4, -6, 2, 1, 3, -1, -1, 2. Remember that this is different than the augmented matrix that we worked on early in this unit. Matrix equation, or a variable matrix, and then the constant matrix over here. This tells me from our work before that XYZ will equal the inverse of this matrix times 7, -14, 0. When you're working on this in your homework, you want to write this down. You want to write out these steps, of course. I'm going to write this so that I don't have to keep flipping back and forth. I want the inverse of that first matrix. Let me show you how to do this on the graphing calculator. Clear all this business out. We want to enter a matrix in. So we go to the matrix menu. Second matrix. We need to edit because we need to enter values in, right? Now my coefficient matrix is 3 by 3. It's that square matrix. 3, 4, -6, 2, 1, 3, and then we had -1, -1, and 2. Okay, that is my coefficient matrix. I want to find the inverse of it. I gotta hit second and then quit to get out of there. Otherwise, if I type anything else, it stays in that matrix. Let's go back to the matrix menu. Under names, I want to select the A. It takes it to my main screen. And then if I hit this X to the -1 power, that's what it uses for the inverse. Even though it's not the -1 power, that's what the calculator uses to find the inverse. That's yucky. Let's go and see if we can get some nice fractions that for this. There we go. That's less bad. Still not pretty. I'm going to write this down. -5 sevenths, 2 sevenths, -18 sevenths, 1, 0, 3, 1 seventh, 1 seventh, and 5 sevenths. Go back to our notes over here. I am going to put that matrix that we just found, oops, I'm out of space, so I'm going to come here. I'm put that matrix that we just found in place of this inverse. -5 sevenths, 2 sevenths, -18 sevenths, 1, 0, 3, and then 1 seventh, 1 seventh, 5 sevenths. We still need to multiply that by 7, -14, 0. Okay. On the ALEKS calculator, I believe there's like a drop-down menu for finding the inverse. All right, I'm going to go up this way now because I'm out of space. I have X, Y, and Z will equal. Remember, now I need to multiply this row by this column. This is a 7 here. -5 sevenths times 7 will be -5. 2 sevenths times -14 will be -4. So I have -5 plus -4 plus 0. That times 0 is -9. Let's do that again with this row times that column. 1 times 7 is 7, plus 0 plus 0 is 7. Now here, 1/7 times 7 is 1 minus 2 plus 0. So really 1 minus 2 is -1. My solution is -9, 7, -1. That's how we can do that on the calculator. We actually can multiply matrices in the calculator by putting this other matrix, this 7, -14, in the calculator, and then just use the multiplication button on your main screen. Back here, let's suppose we put 7, -14, 0 in our calculator. We would just, up here, where we put that A inverse, oops, we would just do this, hit the multiplication button, times, go into the matrix menu and get B, if that's where we stored that other matrix. So you can kind of play around with that a little bit. All right, one more example here. 3, -6, -2, 4 times x, y will equal 4, 8. That's my matrix equation. That means xy is equal to 3, -6, -2, 4 inverse times 4, 8. You could throw this in your calculator, or you could use those row operations to get that inverse. What I will tell you is that this inverse does not exist. Not every matrix has an inverse. Not every matrix has a matrix that you could multiply it by to get the identity. What that means is that we cannot use matrix inversion to find it. It's kind of why these words, if possible, are here. So it's not possible using that technique. You would have to use a different technique, which is why here at the bottom of this, the very last page of your notes that you have, you are going to, we are going to summarize our methods. First, we looked at graphing. This was back in chapter 5. These are methods for solving systems of equations. Then we looked at the substitution method back in unit 5. Then we looked at the addition method. I call it addition method because you add the equations. Some people call it elimination because you eliminate one of the variables. Then we looked at Gauss-Jordan method, and now we have this matrix inversion using the inverse, matrix inverses of a matrix. Sometimes they fail. Graphing doesn't work well if your numbers aren't pretty integers that you can find from using the slope, right, to see where they intersect. Substitution, addition, elimination don't work well with large numbers of variables. Gauss-Jordan's pretty flexible. It works a lot. It'll even tell you when you have no solutions or you have an infinite number of solutions. Matrix, using the inverse of a matrix, doesn't work if the inverse doesn't exist. Okay? Those are our options. That's how we can solve systems of equations. You have a lot of flexibility and things that you can do to solve these equations. So, solving systems of equations. So choose wisely when you are given a system of equations based on the techniques and the reasons for various things that we talked about.